walk out. That's fine.
And sometimes you make it a topic because they were just right across. But then they moved to downtown.
Hey everyone, we're going to get started. This week we have Nika Haghtalab talking about topic modeling.
Thanks. Thanks for the introduction. I'm going to talk about a work called Algorithms for Generalized Topic Modeling. This is with my advisor, Avrim. And basically, there has been a lot of recent work, both in the intersection of machine learning and algorithms, to try to get provable algorithms for topic modeling. So what I'm going to talk about today is actually a new and generalized platform for topic modeling and some interesting questions and directions that rise from this framework. So the availability of data has also come to mean that on a day-to-day basis, we are flooded with information. And most of this information actually is completely unorganized. It's not clear what the topic of this information is. The motivation of topic modeling is to look at this unorganized data and find topics and find some structure that's common in this data to, in a way, try to comprehend and understand the subject matter of these documents. So given a large corpus of unlabeled documents, so we don't know what these documents are about, what we want to understand is what are they about? The topics could be many things. For example, there are documents that are about elections, politics, finances, sports, medicine. There's a large range of topics, and documents are typically about one or more topics. So it's not hard, for example, to think about news articles that are about elections and economics, or about, I don't know, effects of football on your health. So you can see that there are documents that are about many different topics, and what you want to understand is what these topics are, and given a document, what it's about. So that's topic modeling. By the way, feel free to stop me at any point if there are any questions. Traditionally, yes.
Would you be interested in like putting weights on the different topics?
Yes, exactly, yeah. So a topic could be, a document could be 90% about health and 10% about football, for example. So the traditional model for topic modeling is you assume that the models are generated by the following process. That each topic is a distribution over words. We usually describe these by vectors in a high-dimensional space. So each word is one element, one feature in this space. And you're looking at distribution over words that form a topic. And then to create a topic, you first choose a mixture. So you choose, for example, a weighted combination of these topics, 90% about health, 10% about sport. And then you look at the resulting distribution over words. So this is now the general distribution if you had to create a document that was 90% about medicine and 10% about sports. So after this, to create a document, you actually draw some words at random, i.i.d, from this distribution. And that would be the document that you get to observe. And the goal of, traditionally the goal was to actually learn what these topic vectors are. And, or in another word, since we are representing topics as distribution over words, what is this distribution over words for each topic?
So are you taking the distance between the words or distance between the different topics in the same document?
You usually assume, so topics themselves, like these vectors, I'm not sure if this is the question you're asking, but these are usually far enough from each other. So, for example, the distribution of words that you assume is associated with a document that's purely about medicine is very different than something that's about politics. So the documents are the topics themselves are pretty well separated. That's the assumption. Yeah. So yeah, they're not. You could have topics that are too close to each other, but it would be very hard to learn them. So traditionally, what you want to recover is actually what these distributions are. And this was a problem that was formalized in about maybe, I think, 98, yes. People started talking about it a little bit earlier, but the formal framework that was introduced, okay, was by Papadimitriou, Tamaki, Raghavan, and Bansal. And they show that if every document that you had in your corpus was purely about only one topic, and each document had at least 2 words, which is pretty mild assumption, then you can in fact learn these topics. But this assumption of having pure documents is really strong. And for a while, people tried to relax this assumption, but they couldn't. So the decade after this work was pretty much mostly about empirical or practical aspects of topic modeling. And it saw a lot of successful models such as LDA, or after that, dynamic topic modeling, and many different algorithms or kind of approaches to this, like maximum likelihood estimators. So, sorry, I don't know what's happening.
Could be the adapter.
Just don't touch it, I think it'll be easier.
I'm not going to touch it, I think. If I don't touch it, it should be fine. Let's see if it happens again. But so there was a lot of work that was more about the empirical and practical aspects of it, and this work actually was very well recognized. Recently got some Test of Time awards, but the main thing with this line of work was that even though practically it was very interesting, the algorithms were typically either not computationally efficient, or they didn't have guarantees. Then more recently, in 2012, Arora and Moitra showed that you can, in fact, deal with the mixed topic setting if you have a mild assumption on topics, that each topic is associated with some words that are only about that topic, and they will never appear in a different topic. So if you have this assumption, then you can learn. And this was very interesting. And immediately after, there was also work where Anandkumar, Su, Kakade, and Telgarsky that showed that you can even relax this assumption further and work with documents that have 3 or more words. So this is all very interesting. Now we have both practical and algorithms with guarantees. So this is, I think, the right time to go back and think about the model that we started working on. What did the model assume on how the documents are generated? So the main problem with this model was that it assumed that the words were drawn i.i.d. from some distribution to create a document. This is not quite right? Like, if I were to draw words at random, I couldn't even form a sentence properly, let alone a whole document. So this is by far, like, everyone agrees that this is the main problem with this model. You can assume that, well, it's not about words being drawn i.i.d., but that the document is only represented by its bag of words model. So I only care about what words appear and how often they appear in the document. The problem with this model is that it's ignoring all the correlation that exists between words. And these are important in documents. For example, I can have 2 different documents about music, and one is talking more about a violin performance, it's talking about violin and strings, and the other is talking about piano. So you don't really talk about piano and strings. It doesn't even have to be words that appear together at the same time, but more like if you're writing a document describing a solo piano performance, the type of words you're going to use are going to be very different than if you're talking about an orchestra. So these correlations between words are really important in practice, and our model was ignoring them. So what we want to do is instead, rather than representing a document as a distribution or random draws from a distribution over words, we want to represent it in a feature space. So these features could be words or could be phrases, but they don't necessarily have to be independent of each other. So now we have a document that can actually have these correlated features and will be just a point in a space. So a little bit more, just to give you more intuition. So what this tells us is that now we can actually have sentences. We can create sentences. Points can be sentences in a space. And if we can work with sentences, we can assume that maybe we are writing a document by independently drawing sentences. So at least this has a correct grammatical makeup. And allows for those correlated words. Or we can go further and assume that paragraphs are being drawn at random. So at least the paragraphs are meaningful. You can talk about a subject matter. Or even better, we want to talk about paragraphs being drawn, but not necessarily at random. Maybe the second paragraph I'm going to write is going to depend on the first one, but it's going to have some extra information, and it's not going to be exactly the same thing. So this is what we want to do. The immediate problem with, or difficulty with this model is that since the paragraphs are points in the feature space, they are very complex. So the number of paragraphs is large. So if I were to talk about a topic as a distribution over paragraphs, it would be impossible even to represent this distribution, let alone learn it. The problem is that, in fact, because the number of paragraphs is so large, you wouldn't even expect to see the same paragraph twice. Of course, there are cases where you would get to see the paragraph twice. I think we should take anything that Michelle Obama has said outside of this set, because that seems to be repeated. But in general, you shouldn't see the paragraph twice. You would need to get infinitely large number of samples to see that. So our goal is not to actually learn the distribution over paragraphs, but to learn, given a paragraph, to learn to predict what is the makeup of this paragraph. Is it 50% medicine, 50% sport, or is it something else? I want to compare this to something that's more common knowledge to people, which is the PAC platform. In the PAC platform, you assume that you're trying to learn a classifier that's usually separating positive and negative points. And you don't really need to learn the distribution over positive or negative points. You just want to learn the classifier. But the difference here is that in the PAC platform, you assume that you see labeled data, and then you want to separate them. Whereas in the topic modeling, the first thing is that the data is unlabeled. And the second thing is that each document is itself a mixture of different classes. So it's not just positive or negative, but somewhere in between. Are there any questions about this? OK, so the formal framework now would be that we can think about the topics as k-vectors. OK. We want to.
Does it happen every time you
no,
no?
I don't. I don't think so. Let's see. I'm worried if you touch it too much, it might just stop working. Let's see how it goes. OK. So one way to do this is to have k-vectors. Kind of, these are going to be your class vectors, your topic vectors. And each paragraph is going to be some point in this space. And the dot product of this paragraph with the vectors are going to be a measure of how much this paragraph x belongs to each of these vectors. So for example, we can have a function f that takes this dot product and tells us for this dot product, this document is 50% about medicine and 50% about sports. In general, we want these, of course, to sum up to 1. And for most of this work, actually, I'm going to talk about when this f is just the identity, so we only care about the dot product. I will, just in the next slide, tell you how this is similar to the previous traditional topic modeling assumption, but it helps us to understand these dot products before I move there. So we create a document, a 2-paragraph document, by taking 2 points in this space. And we assume that they belong to the same document if their makeup is the same. So they're both 50% about topic 1 and 50% about topic 2. So their dot products are going to be the same with all of these vectors. And we allow for some noise. So maybe this doesn't have to be exactly the same. There's going to be some noise, and we can deal with that. So our goal is, if I'm giving you a lot of these 2-paragraph documents coming from some distribution, can you learn these V1 to V8? Is this clear? So this is the feature space, and these topics are going to be just some vectors in the feature space.
Sorry.
Yeah.
Sorry. Can you go over the same mixture weight assumption and what that means?
Sorry, could you say?
The same mixture weight assumption.
Yeah, so it means, for example, if I had a paragraph that was 90% about one topic and 10% about the other topic, every other paragraph in that document is also 90% about the same topic and 10% about the other topic. So in a way, if you're making, it is an assumption that if you're making a document that's 10% about topic 1, 90% about topic 2, every paragraph has the same, more or less the same makeup.
Because there's some noise as well, right?
And some noise. We can deal with some noise, that's true. But that's what the assumption is. Alternatively, you can, instead of taking these V1s and thinking about the dot product, you can take their pseudo-inverse and talk about these vectors A1 to AK. So if you take those, in a way, X would be a convex combination of them. Or rather, more generally, you take a paragraph X, and then you project it down to the subspace that's being spanned by A1 to AK. And it's going to fall in the convex hall of these A1 to AK. And the weight of the convex combination is going to be the weights that are corresponding to the topic mixture.
So when you say like their pseudo-inverse or whatever, do you mean like if I take the matrix with V1 to VK as rows, the pseudo-inverse has rows A1 to AK?
Yes. So in a sense, A1 dot V1 is 1, and 0 for the other ones. Yeah. So it's kind of easier to think about these A1 to AK. So in a sense, the previous model said that these topic vectors were A1 to AK, and then we added them up, and then we took something at random from them. But our current model is slightly different. It says that, sure, take the topic vectors, mix them up together, but then add some noise to it. And this is only what's happening in the span of A1 to AK. Outside of the span, you can have many different things. So this is the difference between the two models. This is the way that our current model is, in a way, generalizing the previous model. Are there any questions about this? OK. So there are other examples as to when, other than topic modeling, that this platform actually come into play. For example, in the co-training platform of Blum and Mitchell, you assume that you have a binary classification, and you don't see the labels, but points appear in pairs. And you want to learn a classifier. So in that case, you can think of that partial membership function that took the function of dot product was actually just a sign function. So it was just positive or negative, because every point was purely in one or the other class. Another thing is that many unsupervised models of learning can kind of fall into this framework. For example, if you have a mixture of Gaussians and you want to learn them, you can, in a way, divide the space to two random set of features and just try to learn the mean in each of those subspaces. OK, so I want to just show you, if you didn't have noise or you were in the nicest setting, how you can deal with this problem. And then we can talk a little bit about how you can deal with noise and lift some of the assumptions. So as a warm-up, assume that you don't have any noise. So the two views, yes?
I may have missed this. So for the function f that takes the dot product as input, what are examples of f except identity or sign? Like what are natural examples to think
So
of?
actually, monotone is pretty standard, just assuming that f is some monotone function. But the other ones also are these like smooth sign functions. So I would say these are the most common set of examples that you want to think about. But especially when I think in topic modeling, monotone is what makes sense. You know, the higher the dot product, the higher is your correlation with that topic. OK, so we want to talk about the case where there's no noise. And let's just assume that also you have some documents that are pure, because that will help us. We will relax both of these assumptions. So in that case, you can think of, let's look at the convex hall of A1 to AK. So each document is shown by two paragraphs that, if you look at them, they will kind of project to the same place in this convex hall if you project them down to the convex combination, to the subspace. So what you want to do is, like, given all of these documents, each one is in a way perpendicular to the subspace. We want to learn what that subspace is. And then once we learn the subspace, we have these documents that are going to project to the corners of this convex hull, and then if you can find those corners, in a way, you're finding the topics. So that's kind of a simple idea that we want to do. So the plan is to first find the span, the subspace, and then project down to that subspace and look at the extreme points. I know this is very simple, but I actually want to go through it because I think it helps to look at the ideas before we lift those assumptions. So let's look at how we can find the subspace. So we said that the reason these are perpendicular to the subspace of span by A1 to AK is that they had the same mixture. So you can think of x1 minus x2 as being in the null space of V1 to Vk, which is the same as the null space of A1 to AK. So you just want to find that null space. So the way you can think about it is that you're going to get all of those vectors, and you want to find a space that is perpendicular to them. So how are you going to do that? And once you do it, you're going to do this projection. But how are you going to do that? There are many different ways of doing this, of course. But something that might help us to think about is that you want to take this null space, so you can look at you can put all of these x1 minus x2s in a matrix and look at their singular value decomposition and take the last k singular vectors. Those are the singular vectors that actually had a 0 singular value, which meant that they didn't appear in that space. So if you can take the last k, then that's a null space that you have found. So you can look at, or the last k eigenvectors of this matrix, and that will be the null space. So once you find that, you can easily project down. Is that clear? Good. So once we have this projection, again, something we want to do is that we want to find the extreme points of this projection now. How do we do that? There are, again, multiple ways of doing this, some faster than others. One algorithm that's easy to think about, it's actually not the fastest algorithm, is to, for each point, take that point and check whether it's going to be in the convex combination of others. So for example, this point in the middle is the convex combination of the corners, so it's not going to be an extreme point, so I can throw it out. But of course, points that are in the corner will pass this test. They're not convex combination of other points, so they will remain in our set, and they're going to be our extreme points. So if I do these two steps, what I have is that the simple two-step algorithm will find the null space and will give me the extreme points. And you can show that even when these, so in this case, the simple case of having no noise and having pure documents, you could take about of an unlabeled document and do this and learn exactly what A1 to AK were or V1 to VK were. So this is the simple algorithm with simple results. Are there any questions about this?
So is the number case up beforehand? Like, so it's like before you start, you know how many topics you're looking for?
For this case, you don't need to do that because you just, once you find, you can look at the extreme points. You will have many copies of each point, but you know they're all projected to the same point, at least on the extreme points, right? So you don't need to know K. When we deal with noise, you either have to know K or you have to have some understanding of how well separated these topic vectors are from each other. So you need to know some information. Usually this is an assumption that, for example, the topic vectors are far enough from each other. So if they are far enough, then you don't actually need to know the number of them. Yes?
So you use like a VC dimension bound to get to the...
For the sample, the number of samples that you need? In a way, yes. So there are some assumptions that I'm hiding here. For example, you need to have some assumptions on the distribution that says if I take the first view minus the second view, I'm not getting just like the null vector every single time. So you have some assumptions on the distribution, and then to say that those assumptions hold on your sample set, you need to talk about VC dimension. Okay, so this was the simple case, and we want to I want to just give you pretty much just flavors of how you would lift these assumptions without going into too much details. But so let's start talking about them. So what are the assumptions that we want to get rid of? we want to assume that there are almost pure documents rather than pure documents. This is actually quite standard when you think about topic modeling. For example, the practical algorithms, the practical models that I was telling you about, LDA, they work with a different set of parameters, and usually the parameters are set in a way that you assume that there is significant weight on documents that are almost purely about some topic. So this is quite standard, so we are going to assume that. And what we want to assume is that each paragraph is affected by some noise. In particular, we're going to look at Gaussian noise, and we are going to assume that the 2 paragraphs in a document are independently affected by Gaussian noise. So we are going to look at when we start with a paragraph, there is a chance that that paragraph is not going to be affected by noise at all, which means that that paragraph was a very long paragraph. It didn't have noise in it. Or it could have been a short paragraph, and it was affected by some Gaussian noise. So actually, before I talk about the required changes about the algorithm, is the setup clear?
Is there a reason why you call them long and short documents? Is that just like an intuition as to why?
It's just an intuition. Because we were saying that when you have short documents, even in the original case, the short documents were the cases that you were drawing words at random. So that means that you have a lot of noise. But if you had a long document, then you don't really have either that much noise or any noise. So that's just the intuition.
Yes. How do you go from a document to a vector?
So you go from paragraphs to vectors. You assume that a paragraph is a point in a feature space.
How do you do that?
The feature space, it's given to you. So, but these features, if you want to think about the practical aspect of it, these features could be the words that are representing the paragraph, or some phrases that appear. It could be anything, but the simple case could be that they are words. The important part is that these features are not necessarily independent of each other. So then, once you have a representation of a paragraph, you say that a document is represented by 2 paragraphs that have similar mixture weights. Okay, so let's just think about what's the problem with the previous algorithm and how we can fix it. So the previous algorithm, we said to look for the null space of x1 minus x2. So the problem there is that, so if I start with this case that none of these paragraphs are actually noisy, and then I add some noise to them, then this x1 minus x2 is not perpendicular to my subspace anymore, right? So I can't necessarily find, like even the null space of x1 minus x2 is not even necessarily k-dimensional. So we want to make sure that if we have enough samples, this is not going to be a problem, that we can still find something that's approximately that null space. So that's one problem. And another problem is that the extreme points projections are kind of messed up. So if you start with, again, something that's not affected by noise and add some noise to it, then you can project it, and you see that it could be projected far outside of this convex hull. So if you were to just take the extreme points of your projections, even if I gave you the null space, if you were to take the extreme points, then these extreme points are not going to be representative of your topic. So these are 2 things that we need to take care of. So let's start talking about how we can take care of the first problem. So previously we said that we're going to take the last k eigenvalues of this matrix. And in fact, what we're saying is that you can still do the same thing. It's still a valid subspace that's close to what you wanted before. And the reason is that, let's look at, just based on how the documents were generated, we can say that the noisy difference between the 2 paragraphs in a document is pretty much the old difference plus some Gaussian noise. And let's see, let's call these just for, because it's easier, let's talk about them as differences. So then in expectation, at least, you can show that what happens is that in expectation, these 2 matrices are very much the same, except that their singular values were shifted down. So in expectation, I can show that this is going directly from this line. You don't actually have to do any computation. You can show that these two matrices are exactly the same, but plus some noise. And what happens is that if you originally started with something that had that the least non-zero singular vector, singular value was large enough, then the order of your singular vectors or eigenvectors are not going to change. So this space in a way is being preserved. So what you're saying is that the assumption, which is very, very mild, that anything in your previous subspace had enough, in a way, enough height, means that you can still take the k eigenvectors, the last k eigenvectors, and you can still work with that setting. And because their order hasn't changed, in expectation, they're in fact the same, they're spanning the same subspace as before. Well, the problem is that we are not in expectation, we are actually in reality, but that's okay. We can use tools from both matrix concentration and VC dimension theory to show that, in fact, even in reality, we are quite close. There is some error term in both cases, but we are quite close. And you can show that from, again, tools from perturbation theory, that if you're very close, then really your projections are going to be off kind of proportional to how close you are. So you can show that together using these tools, you can show that the error of this projection is going to be the difference between these two sides of this inequality, proportional, and that's going to be proportional to your error. So that's kind of a high-level reason for why you should be able to still use the last k eigenvectors, and you're still fine. And if you use those and you project down, your projections have just moved a little bit. In fact, you can make this epsilon, this error, as small as you want by taking more and more samples. So you have a lot of control over that. So this is, of course, very high level, but are there any questions about it?
So why can't you just subtract the sigma square identity?
Sorry, I can't hear you.
You can just subtract the variance from the sigma.
Because I don't want to know the variance.
I think that can be estimated from.
Well, it depends. You can. So I am hiding some stuff here. For example, we are talking about you're going to do a projection on the space. And the error is also going to depend on how far you were from like how far perpendicular you were to this space. So the sigma is going to actually be different for different points. So I am hiding some details, and because of that, you don't want to actually assume that you know sigma or you want to estimate it, but rather if it was like it's pretty standard to assume that you had enough height from your subspace. So the least significant non-zero eigenvalue was still significant enough that still if you do this trick, you're not going to lose those dimensions.
So the current point actually says if sigma is not zero, no matter how many data you have, you still have a non-zero impact.
Sorry, can you?
I mean, if sigma is not zero, then no matter how many data you have, your error is still going to be non-zero.
Yes. The error is going to be non-zero, but you have control over the error. So if you can take more and more samples to reduce the error more and more.
But the error cannot be lower than sigma squared. Like no matter how many data points you have, because you have a sigma squared.
No, so I think that's actually the trick that goes here. So once you show that the space doesn't change, so once you show that the order of the eigenvectors don't change, because you're still working with the same subspace, in a sense, if you were going to project on that subspace, or you were going to project on the subspace that had two sigma square additional things in it, your projection is still the same projection matrix. So this error is actually the error in the projection matrix. It's not going to, it doesn't have to be more than sigma. But I think we can talk about, I can take this offline. I think it's a little bit easier to actually show it to you more mathematically. Yes.
Understand. How did you get a matrix all of a sudden?
For
I don't understand where the matrix came from.
this matrix,
Yeah.
it's just you put each column of it each column of this matrix is one of your samples, the paragraph in one of your samples. So X1 is the matrix that has the first paragraph of all of the samples that you've got as columns. And X2 has the second paragraph.
And then you're doing leverage scores or something?
Sorry, what?
When you say concentration, you said you meant leverage scores or something like that?
For concentration, I'm using the matrix concentration bounds by trop mainly. There are different concentration bounds that I'm using. So you can use Bernstein, you can use matrix Chernoff. There are different bounds that will help you with the matrix concentration. Okay. So this is kind of the overall idea of how you can deal with noise, at least for finding the subspace. Now let's talk about the problem with the bad projections. So the problem was that we could have these projections that are pretty far outside of the convex hull. And we want to be able to at least detect them and get rid of them before we start taking the extreme points. So how are we going to detect them? You can think of, let's even assume that my subspace that I found was a little bit noisy and a little bit wrong. So how I'm going to do this is, if you look at the points that used to be close to pure documents, since some of them were long enough, there is some density, like some points are being projected in the same area. So this area has some density that's not necessarily too small. But if I look at, and because it's capturing all of the nearly pure documents that were non-noisy. But if I look at points that are quite far, those points are for sure noisy points. And because they were for sure noisy points, in a way, the ball around them is just capturing noisy points. So it's capturing some small dissection of this Gaussian. So you can show that because this is by choosing the right size of the parameter for this radius that you're looking at, you can make sure that that ball has a very small density because it's capturing a very small part of a Gaussian distribution. So in a sense, these red balls are going to have a small density, and the blue balls are going to have more density than the red ones. So you can identify the areas that are for sure noisy and are pretty far outside of your convex hull. And once you do that, you can clean up these projections by, well, first removing those points that didn't have enough points in their neighborhood. And you can show that once you remove them, the convex hull didn't change too much because you only removed points that were far outside of convex hull. So the convex hull is still kind of in the same shape. The extreme points were definitely not removed from that convex hull. So this is like a preliminary step to at least clean up some of those projections, get rid of those very bad projections that were very far. And since Ellen asked earlier, again here you're having some assumptions about the distribution. So I'm saying that I should expect to have low density in these small balls. And in reality, again, using tools like VC dimension, you can show that even in reality, all of those balls really captured a few number of points. So in reality, I can still detect them and I can still get rid of them. So once you get rid of them, you still have to find these corners, but you have a convex hull that's now kind of flat. Because there are still some noisy points, like these red points that are still outside. Yes?
Yeah. Those balls you drew, will the size of the ball depend on the sigma, the standard deviation?
No, it doesn't have to depend on sigma, but it depends on the epsilon that you achieved in the previous step. It depends on how much noise your subspace has. Are there more questions about
this?
this?
But I guess that epsilon, no.
That epsilon doesn't have to because we said that you can just take more and more and more samples.
Is there like a thing dependence, like 1 over epsilon squared is the number of samples you need to get in there?
Yeah, so you're going to have something like n over epsilon square and some dependence on sigma, of course, in your sample complexity. Okay, so we got rid of those red balls, and what we have is that we still have to talk about extreme points in this convex hull that's quite flat on the corners, and how can we do that? So before we used to say you can take extreme points by just checking whether a point was in a convex hull of other points. So this is not really going to work for us because it's not resilient to noise. So what we want is to change this slightly, and we are going to say that it's not close to the convex hull of the points that are far from it. Let me just explain it to you on an example. So if this is my kind of the flat convex hull that I have, these corners, I want to be able to distinguish them. So let's take a point that's at this corner, and let's get rid of any point that's close to it. So now we are only considering points that are far from it. And let's look at the convex hull. So in addition to whatever was here, this blue area is also the convex hull of these far points. Now, is my point close to it? Not really. It's far enough. Now let's look at a point here. So this, we want to make sure that this is not distinguished as a topic or as an extreme point. So we want that to fail this, to actually pass this test. So we are going to take the far points. So get rid of any point that's close to it. Look at the convex hull again. Now, is this close to the convex hull? Yes, it's in fact right inside it, but it is close. So if you do this test, you can see that this test will distinguish the points that used to be kind of at the corner or they're close to the corner, and points that are not, and they are really in the flat areas. So once you do this, you get maybe many points here, many points here, many points here, and then you're going to just cluster them together and say all of them together is one topic vector. All of the other ones together is one topic vector. And in a sense, this is like giving you approximately the extreme points, but finding them in this kind of a convex hull that has flat corners. Are there any questions? Is the intuition at least clear? OK. So together, what this showed is that what Nick was also asking, this says that if you take about n over epsilon squared, there are many other parameters in there, points, then you can do the first step, which was take the last k eigenvectors, then clean up by taking, for each point, if you look at some O of epsilon neighborhood of it, if it doesn't have enough density, throw it out. And then do this approximate extreme points, find the approximate extreme points. Again, the area that you're looking at when you're looking at what it means to be far or close, it's again going to be some O of epsilon. And you can show that if you do this with high probability, you can recover these A1 and AK to some epsilon error. So the topic vectors you're going to find, they are very close to the previous topic vectors, but not necessarily the same. So this is kind of a high-level idea of how to get rid of those assumptions and still get something that's meaningful. So I want to actually, before we finish, I want to talk about an open problem that I think is very interesting. And it might be interesting even to people who are not necessarily in learning theory. Are there any questions so far?
What's your dependency on the sigma in your class?
So I think there's a sigma to the power 4 dependency. And actually, no, sorry. I think there's a 1 over sigma squared dependency, if I'm not mistaken.
And you can still make it epsilon as soon as possible, right?
For any sigma, we can get any epsilon. I need to check the dependency because I think there are two terms. There's a sigma to the power 4 and there's a sigma to the power of 2, but I need to remember that. OK, so for one open problem that I find it very interesting is that what if all the paragraphs were short? Or as we said, every single paragraph was affected by the noise. Because we kind of assumed that some paragraphs were still long, and that really helped us with recognizing what points were really far outside of the convex hull. So now we can't do that trick. And maybe a simpler way to think about this is that forget about documents, forget about topic modeling. Let's say you have a distribution over a convex hull of some points. And there's significant weight on the corners of this convex hull. And each point, you first draw it from this distribution, and then you move it by a Gaussian noise. Can you recover those extreme points? So this is actually a variant of a problem called mixture of K-Gaussian. This is a very interesting problem. So in this problem, you basically have a bunch of centers, and they each have some Gaussian noise around, some Gaussian distribution around them, and you look at any point is a mixture of these two Gaussians. For example, it's 10% from this class and then 90% from the other class. And what you want is to find the mean of these Gaussians. But for the problem of finding a mixture of k Gaussians when k is equal to 2, Dasgupta looked at it at 2002, and then later on, more robust algorithm by Kalai et al. In 2010 shows that you can always, if it's just if you just have two Gaussians, you can always find their mean. So for us, if we only had two topics, we could find their mean because they would be the two extreme points. But when k is bigger than 3 or equal to 3, you can show that, people have shown that, Moitro and Valiant showed that you need exponential number of samples to find the mean of these Gaussians. So, but the problem we are looking at isn't that necessarily to find every mean of every Gaussian, but just find the ones that were the extreme points. So if we had a convex hull and we had some points, I just want to find the extreme points of them. In fact, the most difficult cases for k greater than 3 are cases like this, where there is a Gaussian sandwich between two others. So it's hard to learn what the mean of it is. So what you're saying is, let's forget about those Gaussians. I just want the extreme points. Can I do that or not? So I think this is a very interesting open problem. So other than that, let's just, before we finish, review what we actually did in today's talk. So I introduced this generalized topic model that it was more realistic. It allowed us to work with correlated features and create actual meaningful documents. And it was a generalization of the more traditional topic modeling. We showed how we can handle noise, especially when there are some long documents. And we said that when every document is short, for example, the case of 2 or 3 words that previous work knows how to deal with, we can't quite deal with, but that's the open problem that seems very interesting. More generally, we showed that this framework is actually a generalization of code training that relates code training and multi-view learning and topic modeling all together. And even for partial membership function, that function f that we talked about, the function of dot product, so we showed how we can deal with it when it's identity. In fact, we can show similar ideas work when f is just a monotone function. But going forward, there are also interesting open directions there coming from machine learning, which is what happens if that f was a kernel function? Or what if it was a step function? So when it's a step function and it's just a binary classification, that's the co-training setting. But what if k is greater than 2? These are all very interesting questions that are left open. And with that, are there any more questions left? Thank you. Yeah.
So if you had multiple paragraphs in a document, they would all be aligned along the same perpendicular. So
in a non-noisy case.
Yeah. Oh, yeah. But in the noisy case, you could potentially use them to achieve better accuracy because you'll have more data points along that line.
Yeah. So the way you can think about it, so that's one thing you can do. But if you have more than 2 paragraphs, just for each 2 paragraphs, put them in one document, another document, another document.
Oh,
but yeah. So if the number of views per document was large itself, you could denoise even better. That's right.
And is there a dependency on the dimensionality of that feature space? Like the
N?
feature space you're given?
Yeah, so we assume that feature space n is the number of features in that space.
Oh, okay.
Good. So maybe let me clarify this. So what I showed you was an upper bound of n over epsilon square. That is, in fact, n over epsilon is required. And you can show that there's a lower bound for it, but you can have additional assumptions about these topic vectors and the distribution that allows you to go lower than dependence on n. Like maybe you can go have a dependence on k, but you need extra assumptions.
And is there a dependency on the correlation between those features? Like if the underlying features are highly correlated, then
So in a way, we are ignoring that, but just assuming that we have some assumptions on the correlation, on the covariance matrix of the documents. But other than that, we are ignoring any other assumption about the correlations. Yes, sir.
So let me ask you an extremely naive question. So, I mean, I could imagine doing the same thing for something like images, right, where you're working pixels or something. But there, it seems like the correct thing to do is you're supposed to do some crazy deep learning thing, and then you're going to be able to have a computer sort of classify your images extremely well, and or I mean, maybe surprisingly well. So why is that not what you should be doing here? Like, what's special about documents that you want this very explicit algorithm as opposed to?
Yeah. So there are many different things that I can give you as answer. One is that what we're working here is unlabeled documents. There's a lot of unlabeled documents that's available, but each document itself looks like it has different parts. So the fact that it has different parts, that there's some measure of consistency between them, helps you give provable guarantees for learning what the structure of the document is. On the other hand, images is kind of, I can't think off the top of my head a way of saying that and two images always appear together, or they represent the same thing.
Because my main question is like why you don't expect some sort of deep learning approach to be effective for documents.
Deep learning has no terms.
Okay, so yeah,
So
I agree, that's an answer.
So yeah, so another answer would be that there's a practical line of algorithms but without guarantee, that look at many different things to do. So, but this is like looking at algorithmic questions, yeah.
Right, I accept that answer. The answer is you just want something with guarantee.
Yeah. But also I think especially like when you're talking about images versus documents, because documents are naturally multi-part.
Of course, yeah.
But images, I don't think they're naturally multi-part.
So practically do deep learning things, are those the champions for document things too? Or?
I don't think, I haven't seen deep learning. There is some for multi-view deep learning that people might be applying them, but I think they're mostly, I think they do maximum likelihood a lot and variance of it, if I'm not mistaken. Yeah.
And with this, and is this practical now in some sense? Like, can you run, like, can you actually?
It's practical as in you can do it. We actually haven't done any experiments, but the algorithm is simple and it's relatively lightweight. You can, it has provable guarantees and it has computational. The assumptions seem very natural. Even the assumptions that I hid from you are very natural. Yeah.
So for the last open problem you mentioned, can you tell me where the following intuition fails? So you said we shouldn't worry about the result of Muitra and Valiant because we just care about learning the extreme means and not everything. But at least in the case of Gaussians, like if we could, in the case of 3 Gaussians, if we could learn the extremes, it seems it would be pretty easy to then learn the third Gaussian, like the third mean. So I don't see why we shouldn't worry about the hardness of learning 3 Gaussians as an obstacle to this.
Yeah. So it's not that we shouldn't learn about the hardness of learning them. It's more about the hardness there doesn't say that you can't. So the problem is that even if you learn the extreme points, you now need to remove some points if you want to sort of inductively look at inside. Is that what you're suggesting, right?
Right, exactly.
But the thing is that you are removing the extreme points, but how do you know whether a point originally came from the distribution that was associated?
So what you're saying is if I had 3 Gaussians and you told me what the means of the 2 extreme ones are, I still wouldn't be able to say what the mean of the third one is?
Well, what I'm saying is that if I tell you the extreme points, if I give you a convex hull and tell you the extreme points of it, you still can't necessarily distinguish a Gaussian that was in the middle of them. At least I don't think any result says that. Maybe you can. That's to me still an open direction. Because you really have to disentangle these Gaussians. It's not that once you find the center, you know exactly what points went to that center. They're still very much entangled. Yeah. Are there any more questions?
Thank you.
Thank you.